The moment distribution method can be used to analyze indeterminate frames that can sidesway. That is, the nodes move. The key is that we need to superimpose multiple analyses. So in this problem we will use moment distribution to analyze an indeterminate frame that can sidesway. And the key concepts are constructing a system of superimposed loadings to replicate the behavior of a sidesway frame, determining fixed end moments, and applying moment distribution to predict moments inside frame members. And here's our frame. It's a simple portal frame, which means that it's fixed at base A, fixed at base D, with fixed connections or rigid connections at B and C, and we have a uniform distributed load acting horizontally on the frame. Our goal is to determine the moments at each joint or support. And for this frame, the modulus of elasticity and moment of inertia are constant for all three members. And here's our approach. First, we'll begin by approximating the answer. Then, we'll find stiffness and distribution factors. Which are dependent upon the geometry of the problem. Then we'll identify what are the cases that we need to superimpose. At that point we'll be ready to apply the moment distribution method for the restrained frame. Which is one of the cases we'll superimpose. Once we've completed that analysis problem, we'll find the restraining force. Then it's time to apply moment distribution. For the unrestrained frame. Which is the other part of the superposition. Once we have results in 4 and 6, we'll be able to find the moments in the frame. That being the original frame. So we'll have to superimpose our results. Then, to ensure we have reasonable results, we'll compare with the approximation. Step 1. Let's approximate the answer. Moment distribution for a sidesway frame is going to be a lengthy process, and there will be opportunities for math errors along the way. So we're going to want to have something we can compare against at the end to judge the reasonableness of our results. And so here's what we'll do. Let's assume that the distributed load acts as concentrated load at the nearest support or joint. Which means our situation will look like this, where the point force is the 6 kips per foot times half the height which is 54 kips. And so at the bottom it would be 6 kips per foot times 9 feet, 54 kips. But that goes straight into the foundation. So if we look at this rigid frame with a point load at the top and it's able to sidesway, let's use the portal method for analysis. So I have my frame, node A, B, C, and D. And the assumption is that there are inflection points mid-height of the columns and mid-span of the beams, and I'll label these points E, F, and G. We have our horizontal load of 54 kips. So now if I cut it at the inflection points in the column, we have a shear V, another shear V, because the shears at the exterior columns are equal and the interior columns, which we don't have any, would have been equal but twice as large as the exterior. We have our horizontal force, and we'll sum forces in the horizontal direction. Choose to the right as positive. We have the 54 kips minus 2 times V, so the shear in each column is 27 kips. Now to find the moment in the columns. So I'll draw a free body diagram of member AE. It is 9 feet tall, has a horizontal reaction, a moment reaction, potentially a vertical reaction as well, and a shear of 27 kips. The key is I want to find the moment reaction. So let's sum moments about point A. I'll choose clockwise as positive because that's the direction we draw our moments when we apply moment distribution. And so I get a positive contribution of the shear mid-height of the column through 9 feet plus the unknown moment at the end of the column MA. So MA we think will be approximately minus 243 foot kips, or clockwise is positive. Now from the symmetry, the shear at the top of GD is the same, the height of GD is the same, so the moment at D we think will also be negative 243 foot kips. Now a free body diagram of EB, the top part of the column. It is also 9 feet. We have the shear of 27 kips, unknown shear at the top, and unknown moment at the top. So let's sum moments about point B. Again, I will choose clockwise as positive for my summation. We have the unknown moment plus a positive contribution from the shear at mid-height of the column. So moment BA will be approximately negative 243 foot kips. And likewise, the moment at CD will also be negative 243, or something similar, we think. So now we have something we can compare to at the end of our moment distribution analysis. Now step 2. At the beginning of moment distribution, we need to find the stiffness and distribution factors. First, the bending stiffness. Since all ends of the various members of this frame are either fixed supported or continuous, and because they're prismatic, the stiffness is the same at both ends, and it's 4EI over L. For member AB, L is 18 feet. For the beam member, 4EI over 24 feet. And for the right column, 4EI over 18 feet. Now the distribution factors. Distribution factor for AB is 0 because it is fixed supported. So when we release node A, all unbalanced moment goes into the support, into the foundation. None of it comes back into member AB. Likewise, at D, in member DC, we have the same. And these are all since they're fixed supported. Now how about node B? Well, to find the distribution factors for node B, we need to sum all of the stiffnesses at node B. So we have stiffness BA plus the stiffness BC. That equals 4EI over 18 feet plus 4EI over 24 feet. And together, if we find common denominator, add these up, we get 14EI over 36 feet. Which means that our distribution factor, BA, the percentage that will come back to member BA when node B is released, will be 4EI over 18 feet divided by 14EI over 36 feet. We evaluate that expression and find 0.571 is the portion that distributes back into BA. For BC, it's 4EI over 24 feet divided by 14EI over 36 feet, and this is 0.429. These two quantities add up to 1.0. That's a good intermediate check. Node C. Sum of all the stiffnesses at node C is KCB and KCD. Ooh, that's a plus. Plus KCD. So that equals 4EI over 24 feet plus 4EI over 18 feet. And again we get 14EI over 36 feet. So the distribution factor for CB is the stiffness member CB over the stiffness for the entire joint or node, and that's 4EI over 24 feet divided by 14EI over 36 feet. Now if you noticed the similarity in the stiffnesses at the two nodes and said, we're going to get the same results. You're absolutely right, but don't get them accidentally reversed. Distribution factor for CB is 0.429. The distribution factor CD for EI over 18 feet divided by 14 EI over 36 feet is the one that will give us 0.571, and of course these add to 1.0, and so they check as well. Now step 3. Superposition. Our frame looks like this, which has the applied load, but it will move. These two nodes will shift to the right, and so we're going to need to superimpose two situations in order to apply moment distribution. The first, we will restrain the frame so that when we apply the loads, we get a reaction, and then we take the same frame, strip off the applied load, and to make these two add up to this one, I need to apply R in the opposite direction. And so these are the two situations we need to analyze. And now step 4. Let's perform analysis of the restrained frame. Just so that we're understanding my terminology, this is the restrained frame, this is the unrestrained frame. Okay. There will be sub-steps to this process, and so we'll start by finding the fixed end moments. frame looks something like this with our uniform distributed load. So we need to find our fixed end moment at AB. Fixed end moment at the other end. Our fixed end moment BC in the beam on top. Fixed end moment CB at the other end. Fixed end moment CD. And fixed end moment DC. Let's start with member AB. Fixed on both ends, uniformly loaded in between. When we look on the inside back cover of our text, we find that situation shown here. And so our fixed end moments are omega L squared over 12 at each end. But note the directions shown. At this end, it's counterclockwise instead of clockwise. So the fixed end moment, AB, is minus omega L squared over 12. And that equals a minus 6 kips per linear foot times the 18 foot length squared over 12. Put that together, we get a minus 162 foot kips, where clockwise would be positive. At the other end of that column, it's a positive omega L squared over 12. And so that's positive 162 foot kips. For all our other members of the frame, we have no loading in between the fixed ends, so all of those fixed end moments are 0. Now we're ready for step 4b. We're going to apply moment distribution. And I've created a worksheet in which we can put all our information. So we need the distribution factors. For joint A, we saw the distribution factor would be 0 because it's a fixed support, which means it's true at D as well. For BA and BC, we have these distribution factors. And for CB and CD, we have those same distribution factors reversed. So we have 0, 0.571, 0.429, 0.429, 0.571, and 0. And I pushed these two together, and I pushed these two together because they all belong to the same node. These two are not part of the same node. Now, I'll add a second line because everything below this will be a moment. It'll have units of foot kips, and instead of cluttering our worksheet with a bunch of units with the numbers, I'll use just the numbers. So we start with our fixed end moments. For node A, we found it to be negative 162 foot kips. At node B in member AB, a positive 162 foot kips, and all the rest 0. So we have a negative 162, a positive 162, a 0, 0, 0, and 0. Now to release a node. There's no need to release node A. It's fixed supported. The distribution factor is 0, so any unbalanced moment at A goes into the fixed support or the foundation. None of it comes back into the member. Likewise, we won't need to release node D either. So let's go to B to start. We take minus the unbalanced moment, and our unbalanced moment is the 162 plus the 0. So we need to distribute a negative 162 foot kips. I take the negative 162 times the distribution factor 571, and I get a negative 92.5. I take the moment we need to distribute, negative 162, times the distribution factor 0.429, and I get a negative 69.5 foot kips. I'll draw a line underneath these two, because now when I clamp B again, all of these add to 0. This node is now in equilibrium. But we have carryover. And because the members are all prismatic, the carryover is half of the moment we just distributed to the member. So when I take half of negative 92.5 foot kips and round it off, we carry over a negative 46.2 foot kips to node A, and we carry over a negative 37.8 foot kips into node C in member BC. Now we're ready to release another node. Let's release node C. Unbalanced moment is the 0 plus the 0 minus the 37.8 kips. Foot kips, excuse me. And so the negative signs cancel, and we need to distribute a positive 37.8 foot kips. So when I take the 37.8 times the distribution factor of 0.429, I get a positive 16.2 foot kips. When I take the 37.8 foot kips times the distribution factor of 0.571, I get a positive 21.6 foot kips. And now I clamp this node back down. It is in equilibrium, but we have carryover. And so half of that moment, a positive 8.1 foot kips, carries over to node B. Half of that moment, 10.8 foot kips, carries over to node D. Again, we don't need to release node D, so we go back and release B. My unbalanced moment is just the 8.1. Everything above this line added to 0. So my unbalanced moment, or the moment I need to distribute, is a negative 8.1 foot kips. I multiply that times my distribution factor and get a negative 4.6 foot kips. I take this moment to distribute times the distribution factor and get a negative 3.5 foot kips. And I'll draw my line here because this node is now in equilibrium. But we do get carryover. And so a negative 2.3 foot kips carries over to node A, and we'll round off to a negative 1.8 foot kips carry over to node C in member BC. We now release node C. It has an unbalanced moment of a negative 1.8 foot kips, which means we need to distribute a positive 1.8 foot kips. I take the 1.8 times the distribution factor, and I distribute a positive 0.8 foot kips. I take the moment 1.8 foot kips times the distribution factor, and I have a 1.0 foot kips. Node C is now in equilibrium, and so we clamp it back down. I'll carry over. We have half a foot kip goes to member or node D, and 0.4 foot kips comes to node B in member BC. An important question is, when do we stop? And I would prefer to stop when the amount of unbalanced moment is less than about 1% of the fixed end moments. In this case, our fixed end moments were 162 foot kips, so we are below, well below 1% now. And so let's go to part C. Let's find moments in the restrained frame. So I will draw another line here to indicate we are summing everything in the column. And so to find the moment in the restrained frame, I take the negative 162, negative 46.2, and negative 2.3, and I get a negative 210.5 foot kips at support A. We add up the next column, the 162, negative 92.5, negative 4.6, and get a positive 64.9 foot kips. We add up this column and get a negative 64.5 foot kips. Now, these are the only members framing into node B. If we sum those up, we get 0.4 foot kips, which is reasonably close to 0. They have to add to 0 for the node to be in equilibrium, but 0.4 is sufficiently a small percentage of these numbers. I'm willing to accept that amount of error, and it's a truncation because we stopped the iterative process. Now let's add up all in this column. We have a negative 22.6 foot kips. Add up all in this column. We get a positive 22.6 foot kips. These add exactly to 0. That's a good intermediate check. We'll add all of these The reaction at B is 11.3 foot kips. Now let me remind you, we're not done. These are just the moments in the restrained frame, and we still need to find out what's the restraining force. So let's find that restraining force. And to figure out how we're going to do that, let's take a look at a free body diagram of our frame. We have the distributed load, R we're looking for, horizontal reactions at the supports, or at the fixed supports at A and D, vertical reactions there, and moment reactions there. Well, to find R, if we know these horizontal reactions, we can just sum forces in the horizontal direction. So let's find each of these reactions. So I'll draw a free body diagram of member AB. It is 18 feet long with the uniform distributed load of 6 kips per linear foot, unknown shear just to the left, or actually below node B, moment BA, which we found to be 64.9 foot kips, the horizontal reaction AX, the moment reaction AB, which is negative 210.5 foot kips, and the vertical reaction AY. So let's sum moments about point B. And I can choose any direction to be clockwise or to be positive. I'll choose clockwise to be positive, since that's the sign convention for our moments. I get a positive contribution from the moment at B, a negative contribution from the distributed load, 6 kips per foot, times 18 feet gives me the force resultant, and that force resultant acts 18 over 2 feet from node B. We have a positive contribution from AX acting through 18 feet, and we add in the contribution from the reaction at A, but it's a negative quantity. Solve that for AX, and we get 62.1 kips positive, so it is to the left. Now we repeat the process. For member CD. It is also 18 feet long with an unknown horizontal reaction dx, moment reaction dc of a positive 11.3 foot kips, unknown dy, unknown shear to the right or below point C, and our moment CD, which we found to be 22.6 foot kips. So we sum moments about point C. Again, I'll choose clockwise as positive. We have a positive contribution from the moment reaction. We have a positive contribution from the horizontal reaction at D, acting through 18 feet. We have a positive contribution from the moment at C, 22.6 foot kips. Solve for dx, and I get a negative 1.9 kips. It is not to the left, but actually to the right. And so now, free body diagram of the entire frame. But to keep our diagram from getting too cluttered, I'm going to draw only the horizontal forces, since we saw that that's the equilibrium we need to apply in order to find our restraining force R. So I sum forces in the horizontal direction. I will choose to the left as positive, since that's the way all my arrows are drawn, at least for the concentrated forces. So I have positive contribution from the reaction at A. There is a negative contribution from the distributed load acting over 18 feet. Positive contribution from the restraining force, and a positive contribution but a negative magnitude for the reaction at D. And I get a restraining force of a positive 47.8 kips acting to the left. Now to perform analysis of the unrestrained frame. So we're talking about a frame that does not have the distributed load applied. Instead, we're talking about a frame with 47.8 kips applied laterally, which will cause a deflected shape like such, so that the ends of the columns will be displaced delta relative to the other ends. But I don't know how far that displacement is given this force. But what we have seen is if I can get fixed end moments for my frame, I can analyze it and find reactions or force applied. So let me, instead of applying a set lateral force and calculating the displacement, let me apply a set lateral displacement and calculate the force required to cause it. Then we can multiply those results by the ratio of 47.8 kips divided by r prime, and we will get the moments in the frame if we applied the 47.8 kips. So let's get our fixed end moments. If we apply an R prime that causes delta prime. So the moments we will need are in member AB, in member BC, and in member CD. I'll do 2 and applied horizontal displacement. Which, if I could draw this well, would ultimately look like this because the joints B and C will rotate. So now let's look specifically at fixed end moments for member AB, and I'll turn it on its side so that it resembles the cases we have inside the back cover of our text. And so for this situation, the fixed end moment AB is given by 6 EI delta over L squared, but notice that the moments for this type of displacement, relative displacement of the ends, the moments are both counterclockwise. So the fixed end moment is a minus 6 EI delta prime over L squared. And that's identical to the moment at the other end. Same sign, same magnitude. Now to keep my math simple, I'm going to choose delta prime such that the quantity 6 EI delta prime over L squared for member AB is equal to 100 foot kips. And so that means that the fixed end moment AB is a positive 100 foot kips, and the fixed end moment BA, I'm going to make that, this quantity is 100 foot kips, so this means my fixed end moment is a negative 100 foot kips, because we saw that the fixed end moment is in the opposite direction that we drew. For member BC, we have fixed, no load in between, no relative displacement of the nodes. So these fixed end moments are identical and are 0. Now member CD. Again, I'll draw it on its side so it resembles what we have on the inside front cover, or inside back cover of our text. And note, since EI over L squared for member CD is identical to EI over L squared for member AB, and because we're applying the same relative displacement to both nodes, or to both members, then the quantity 6EI delta prime over L squared for member CD also equals 100 foot kips, which means that my fixed end moment at end C is a negative 100 foot kips, and my fixed end moment at the other end D is negative 100 foot kips. So why did I pick 100 foot kips? Honestly, because it's a round number. When the unbalanced moment everywhere in our analysis is sufficiently less than 1, then I'm confident it's time to stop the iterations and we can find the moments in the frame. I could have chosen any number, but that's why I chose 100. Now step 6b. We're going to apply moment distribution. Note that the distribution factors don't change. Only the fixed end moments change. Distribution factors are based on geometry of the problem and stiffness of the members. For node A, we found the fixed end moment to be a negative 100 foot kips. And at the other end of that member, we found it to be a negative 100 foot kips. At BC, we found the fixed end moment to be 0, as well as the other end at the other end of the member. In CD, we found to be negative 100 foot kips, and at the other end of the member at node D, also negative 100 foot kips. As with the restrained frame, all of the quantities from the fixed end moments down are in units of foot kips, and so in order to avoid cluttering up this worksheet, I'm not going to write the units. Also, just like with the restrained frame, I don't need to release node A or node D because their distribution factors are 0. So I'll start by releasing node B. And we'll take a negative of the unbalanced moment, and at node B we have a negative 100 and a 0. So we have a moment that we need to distribute of 100 foot kips. I multiply that moment we need to distribute by my distribution factor, and we distribute 57.1 foot kips into member BA. I take the 100 we need to distribute and multiply it by the distribution factor 0.429, and we distribute 42.9 foot kips into member BC. So now we clamp node B again, and it is in equilibrium, but we get carryover to the other ends of the members. So half of the 57.1 we will round off to 28.6 foot kips, carries over to node A, And half of the 42.9, which I will round off to 21.4 foot kips, carries over to node C. Now let's release node C. My unbalanced moment, I have a minus 0 minus 100 plus 21.4. And that means we need to distribute 78.6 foot kips to bring node C back into equilibrium. So I take the 78.6 times the distribution factor, and we distribute 33.7 foot kips into member CB. Take the 78.6 times the distribution factor, and we distribute 44.9 foot kips into member CD. And this brings node C into equilibrium, but we have carryover of moment to the other ends of those members. And so half of 44.9 will round off to 22.4 foot kips to node D. Half of 33.7 will round off to 16.8 foot kips to node B. We don't need to release node D, so let's go back to B. My unbalanced moment is 16.8 foot kips. Everything above this line adds to 0 because it was in equilibrium, so it's only this moment that is unbalanced, and so we need to distribute a negative 16.8 foot kips. So we multiply it by the distribution factor, and we'll distribute a negative 9.6 foot kips into member BA. We'll take this moment times this distribution factor, and we'll distribute a negative 7.2 foot kips into member BC. And now node B is in equilibrium. Again, we'll have carryover as we clamp that down. Moment is generated at the other ends. Half of the negative 9.6 is a negative 4.8 foot kips carried over to node A. Half of the negative 7.2 is a negative 3.6 that carries over to node B. So it's time to release B. Excuse me, not B, but node C. Node B is in equilibrium. A minus the unbalanced moment, which is just negative 3.6 foot kips, and so we need to distribute a 3.6 foot kip. We take that quantity times this distribution factor, and we distribute 1.5 foot kips into member CB. This quantity times this distribution factor, and we distribute 2.1 into member CD. And now C is in equilibrium, and we carry over. This rounds off to a 1.0 to node D and a 0.8 to node B. And we're getting close to a stopping point. Let's release node B one more time. My unbalanced moment is 0.8 foot kips, and so we need to distribute a negative 0.8. I take that times my distribution factor, and I distribute a negative 0.5 to member BA. Take my negative 0.8 times my distribution factor, and I distribute a negative 0.3 to member BC. Now B is in equilibrium. We clamp it down, carry over the little bit that does transfer to the other ends of the members, and so we put a negative 0.2 over at node A and a negative 0.2 to node C. Well, now our unbalanced moments are sufficiently smaller than 1% of our initial fixed end moments. I'm satisfied it's time to stop the iterations and go to part C, which is to find moments in the unrestrained frame. And to do that, we add up everything above the line in individual columns. So for node A, we take the negative 100 plus 28.6 minus 4.8 minus 0.2, and we get a negative 76.4 foot kips at A. We add up column B and get a negative 53.0 foot kips. We add up the column for member BC and get a positive 53.0 foot kips. These are the only members that meet at node B, and so their summation should equal 0, and it does. That's a good intermediate check. We add up this column, and so for member CB, we have a moment of 52.8 foot kips. We add this column and get a negative 53.0 foot kips. These are the only ones that meet at node C. Their summation equals a negative 0.2 foot kips, which is sufficiently close to 0. That's a good sign. We add up the last column, the moment at reaction D, and get a negative 76.6 foot kips. Now in the case of this unrestrained frame, it is perfectly symmetric, and so we would expect the moments to be perfectly symmetric. We have a negative 76.4 and a negative 76.6, and that slight difference is probably due to round off, so we say that's a pretty good sign that they match. And we already looked at the internal equilibrium at the nodes, but also their magnitudes match, and they should from symmetry. That's a good sign. Now for step 6D, we need to find the force R prime that we applied to the frame in order to cause the lateral movement delta prime. And to do that, let's start with a free body diagram of member AB, because we're going to follow a similar process that we used to find the restraining force R in the restrained frame. So we have our unknown horizontal reaction at A, unknown vertical reaction at A, moment reaction we found to be negative 76.4 foot kips, an unknown shear just to the left of point B, and a moment which we found to be negative 53 foot kips. So let's sum moments about point B. What we're looking for is the horizontal reaction at A. I'll choose clockwise to be positive. We have a positive contribution but a negative magnitude from the 76.4 foot kips at A. We have a positive contribution from the reaction at A through 15 feet, and a positive contribution but a negative magnitude from the moment at B. We solve that for A, we get a positive 7.19 kips. It is to the right. Now, free body diagram of CD. It is also 18 feet tall. Have my unknown reaction. My vertical force, my moment at D, which we found to be negative 76.6 foot kips, the shear at D, or just to the right of it, and the moment we found to be negative 53 foot kips. So we sum moments about point C, choose clockwise as positive, a positive contribution but a negative 76.6 foot kip magnitude at D, plus a positive contribution from the horizontal force or horizontal reaction at D, and a positive contribution but negative magnitude from the moment at B, the moment at C. So we find dx is a positive 7.20 kips to the right. Now, from the symmetry of the problem, if there wasn't round-off error in our moment distribution, these two quantities would be exactly the same. But they are reasonably close. Now, a free body diagram of the entire structure. And I'm only looking for horizontal equilibrium, so I'm not going to bother drawing the moments. AX, we found a 7.19 kips. DX, we found to be a 7.20 kips. We're looking for R prime, so when I sum forces in the horizontal direction, and I will choose to the left to be positive, since that's the direction of my reactions. Contribution from A, contribution from D, minus R prime. R prime is equal to a positive 14.39 kips in the direction drawn. Oops, I just saw a bookkeeping error. This is not node D, but instead node C. But that doesn't affect any of our calculations. Now we're ready for step 7. Let's find the moments in the frame. We're talking about the original frame. So to find those, for this situation, we need to superimpose the results we obtained for the restrained frame, to which we add the results of our unrestrained frame, but we need to amplify them by the ratio of R over R prime. because we applied R prime to our unrestrained frame. So to get the moments, we just add up our previous results. For member AB at node A, in the restrained frame we had a moment of negative 210.5 foot kips, and in the unrestrained frame we had a moment of negative 76.4 foot kips. So we have the results from the restrained frame plus the results from the unrestrained frame. We need to multiply it by a ratio. R we found to be 47.8 kips, and R prime we found to be 14.39 kips. We put those together and we get a moment of negative 464 foot kips, where clockwise is positive. Now for the same member, but at the other end, node B, our restrained frame moment is 64.9 and our unrestrained negative 53. So we take the 64.9 foot kips plus the same ratio times the negative 53 foot kips, and together that equals a negative 111 foot kips. Now, same node, but member BC. Even though we know these two numbers should be identical, and they're not, I'm not going to change what we calculated for our result. So I'm going to use the negative 64.5 for member BC at node B, and 53 in the unrestrained frame. So we have the negative 64.5 foot kips plus the same ratio times the positive 53 foot kips, and together they add up to be 111 foot kips. And on either side of the node, since there's no applied couple moment to this frame, and there are only two members meeting at this node, we would expect these two to equal 0. That's a good check. Now at the other end of the member, at node C, from the restrained frame we have negative 22.6, and from the unrestrained frame 52.8. Negative 22.6 foot kips. Our ratio times the unrestrained result put those together and we get a positive 153 foot kips. Now the other side of the node, member CD. The restrained frame had a moment of 22.6 and the unrestrained frame negative 53. So we take our 22.6 foot kips our ratio, the negative 53 foot kips, put those together we get a negative 153 foot kips. And again, there are only two members framing in at node C. There's no couple moment applied at node C. The summation of the two is 0, and that's exactly what we expect. Now the last one, the moment reaction at D. For the restrained frame, we obtained 11.3. Unrestrained frame, negative 76.6. We have our ratio. We have the negative 76.6 foot kips. Together that equals a negative 243 foot kips. Now to find out if all of that work produced a reasonable result. And part of how we'll make that evaluation is to compare with our approximation. We had approximated the moment reaction at A and the moment reaction at D to be negative 243 foot kips. Both of those, our sign convention is clockwise is positive. In the columns, we said the moment at the top of column AB and the moment at the top of column CD would be negative 243 foot kips. Which is not a surprise when you consider we were using the Portal method, which says that the inflection point is at mid-height of the column, so the moments top and bottom of the column will be identical. In our approximate analysis, if we had continued the calculations, we would have obtained exactly the same moment on the beam side of node B as we did at the column side, so we didn't bother with the calculations. Now, from moment distribution, we found the moment reaction at A to be negative 464 and the moment reaction at D to be negative 243. Again, we use the same sign convention, so positive would have been clockwise. Then at the top of the columns, we obtained negative 111 foot kips for the top of column AB and negative 153 foot kips for the top of column CD. So how do those compare? The signs match. Good. The orders of magnitude match. That's good. But the magnitudes, in some cases, appear to be kind of off. Almost double here and almost half here. This one was right on, and this one was okay. So the question is still, is this a reasonable result from moment distribution, or have we made some errors? Let's think about some of the other clues we've had so far. Our intermediate checks all worked out. And let's think about the portal method. We assumed that the inflection point was mid-height of the column. If that inflection point is really a little bit above or below mid-height, it can have a substantial impact on the moment at each of the ends of the column. So if the issue is the inflection point's not in the middle, then we would expect one prediction to be high and one prediction to be low. And in this case, our prediction for the reaction was low. The prediction at the top of the column was high. So that is consistent with inflection point not being at the mid-height of the column like we thought. The other assumption we made was that all of this distributed load really just breaks up into 2-point loads equally. And that's not exactly true either. So I would say these are reasonable results based on all of the things considered. The difference in magnitudes is explainable by location or potential deviation of the location of the inflection point from our assumption. If you're still not convinced, one option is use another analysis method for this frame and then compare results again. Another analysis method you could use is direct stiffness, which we cover in a future chapter. Now let's go back and review the process we followed to obtain these results. We started by approximating the answer. We took the distributed load, considered it to be 2-point loads, one acting at node B and one acting at node A, and we used the portal method to estimate the moments in the frame. We then found the bending stiffness for each member and the distribution factors for each node. In order to apply moment distribution to a frame that can sidesway, we need to superimpose two situations, so we identified what those would be, and we began our analysis of the restrained frame, which began by finding the fixed end moments. Then we consolidated the fixed end moments and distribution factor information into a worksheet and began releasing nodes one at a time, distributing the unbalanced moment, and carrying over to the other ends of the members. We then added up the information in each column to find the moment at each node in each member of the restrained frame. We then use those moments to find the restraining force, R, by applying equilibrium. We then performed analysis of the unrestrained frame. In that case, we don't know what the deflection would be if we applied R, so instead we applied a deflection and calculated R prime, knowing that we would just need to modify our results by the ratio of R over R prime. And so we picked a deflection such that the fixed end moment would all have the magnitude 100 foot kips. The stiffnesses and distribution factors are unchanged between the two situations we superimpose. So we used the same distribution factors, our new fixed end moments, and we applied moment distribution to the restrained frame. We then found the moments in the unrestrained frame by adding up the information in each column, and used that coupled with equilibrium to find R prime. To find the moments in the original frame, we then superimposed the results from the two analyses using the ratio of R over R prime to modify the results of the unrestrained frame. We then evaluated our results by looking at the approximation and how it compared to our moment distribution results, by also looking at the intermediate checks and by considering how differences between reality and our assumptions would affect the results, and found that the difference between our calculated results from moment distribution and our approximation could be explained by deviations from the assumptions in our approximation. And so we concluded that we have a reasonable prediction of the moments in the rigid frame that can sidesway. Well done.